Okay, so we'll go ahead and get started here. As you can see, we have a couple days of review. Then on Wednesday, I'm going with the presumption, okay? Again, that's how I like to say it, a presumption that we won't have class. Then when Thursday rolls around, we only have a limited amount of time because Thursday is an early dismissal. So keep that in mind, okay?
Excited for that early dismissal, Mr. McKinney?
Well, it doesn't matter whether I say yes or no. It's not going to stop it. And yeah, I guess it shortens up the afternoon.
Are you excited for Friday? No school? At least no school for us.
No school for you individuals, yes. Mm-hmm. So let me ask you this. We give you this opportunity. Would someone else want to come up here and explain this? Because for those of you who really have a good understanding, or what you think you might be a good understanding, when you explain this to someone else, that only reinforces this content and really helps you understand this and retain this. Because I think we had this discussion this morning in anatomy and physiology. When it comes to utilizing this vocabulary, we just look at, okay, we have an evaluation, let's just memorize this. Then 15 minutes later, after the class period, we don't remember what it is that we had or were forced to recall. And that's what we don't want to have happen. It does, but we would like for us to be able to recall, retain, and keep that content in there. So, with those, does someone else want to go up there and explain that to your classmates?
I need to make sure I actually know how to do this.
So, let me ask you this. So, we had one of your classmates say, I'll do the bottom one. I would rather do the bottom one too. Why would you'd rather do that bottom one? Well, yes, that's true, but as far as bonding is concerned, is it ionic or covalent, that bottom one? Are you sure it's ionic? Well, yeah, so what if it's cobalt and chlorine? It is a metal and a non-metal. So chances are that would say, yes, that is an ionic bond. Okay? So you'd want to do this one. What is the next one someone would maybe choose to want to try? I'm saying that you have to or that we will, but what is the next one you'd maybe want to try? The top one.
I've only done the last one, that's why I said that.
Okay. So I would presume that we think the bottom one's the easiest. That's true. So then, of the remaining two, which one?
I have one out for the first one I can do, but I don't know if it's going to be right.
Okay. But which, that's fine. Just give me a couple of moments. But of the remaining two, which one do you believe is the most difficult?
I'd say the second one.
The middle one is probably by far the most difficult one.
Can I go do
Okay.
the first one?
Well, we had someone else who had volunteered before yourself. Oh, you said I thought you meant first in. You mean first in the top one? Oh, okay, okay. Okay. Okay, so we have to come up here and hit pause while one of your classmates comes up and performs this. No, because YouTube kind of is, they say no. Okay, so some of your classmates have come up here and walked through these compounds that we see here. And we started from the bottom. Well, this one was the simplest to do because it's an ionic bond, to where a question could be asked is, well, how do we know that this only has 3 valence electrons? Well, you go by your negative ion, That's got a -1 charge. You've got 3 of them. So that means that cobalt would have to have 3 electrons to give away, and it does. So these charges have canceled out. So the chlorides are fine. They've each got 8. Cobalt's got none because it gave its electrons away. Then this top compound here, typically you want to start with carbon if it's present, or if it's not there, then nitrogen, because you want to start with the atom that forms the most bonds, and that would be the case here, that carbon does that. And if you went through a process, you might try to single bond that, but you're just going to run out of space because it just can't do that. Because if you're going to do a single bond, okay, and then you try to bond that nitrogen to here, okay, and then notice that we have 5 other spots, but only 3 atoms to put here. So that would tell you if you put a sodium here and then a sodium here, okay, and then a hydrogen up here, that means we've got 2 spots here that are looking to bond, but there's just nothing there, and we're all out of elements here. So then what this would mean is that since you have 2 electrons here and 2 here, that they're going to form this double bond, and that's what we see here. And that's why this atom looks the way that it does. Then, with sodium nitrate here, what happens is you do have to have 1 double bond in here, and that's what's being illustrated. And this does form what we call resonance structures, but for our purposes, we're not too concerned about what a resonance structure is. All that means is, how do you know that the double bond is on this side? Maybe it's over here. So what that is saying is that maybe that double bond is here, and then we've got an oxygen and a sodium up here, because remember, there's 2 electrons, here's 1, then here's 2 more, okay? So then here's that oxygen atom that's on the bottom, and we're showing you what, again, is an electron or a resonance structure. Okay, so 2, 4, 6, okay? That means this oxygen still needs 1 more dot, and then there's our sodium atom. Okay, so that makes an octet. And then here you have your last oxygen atom. And then also what could happen is that double bond could be on the bottom. Okay, so again, that's what we mean by resonance structures. We just mainly mention that. We don't go too far in depth with that. So then for our purposes, the way that we say this is, well, how can we form this bond here if there's nothing there to go back and forth between the nitrogen and oxygen? And the way that we like to approach it, for our purposes, is this is formed what we call a polar covalent bond, to where the electronegativities of these are pulling these 2 electrons back and forth, that they're still sharing them. That's quite different than an ionic bond, certainly way different because their electrons are given away. With a covalent bond, these are being shared equally. But this polar covalent bond, these electrons just go back and forth and back and forth. And that's what allows that compound to look the way that it does. Because we can apply this same logic to on your paper where you had this compound, okay, or if you had this and it had a -2 charge, okay, or you could say maybe we've got something with something in column 1, and we could say K2SO4. Well, then that's +1. That still balances out. So you said you wanted more examples. These are on your paper. This one is not, okay? But that's something that you can work on if you so choose. Well, that's up to you. Okay, so I'm going to go ahead and erase these. So maybe you would like to go back. If you're watching this, you can hit pause and then go back through that. Okay. So we went through these next two examples that you can see here. Phosphoric acid right here, and then potassium sulfate. Now, what happens is, I want you to think about this. Where are these two elements on the periodic table? Are they close to each other or not close to each other?
Pretty close to each other.
Yes, they're right next door to each other. But the most important aspect is these two elements, okay, the sulfur, okay, then the phosphorus, they're in the third period. That gets to be significant because one of the things you might hear when you go to college is something called an expanded octet, okay? And really what that means is, okay, technically you would not be wrong if you were to take these two electrons and these two electrons and just say, well, I think that they should be here and here. And then you're looking at that, you'd say, well, that's 4, that's 8, that's 10, that's 12. It really can't do that. That doesn't satisfy the octet rule. But when you go to an expanded octet, which these elements can do because they're in the third period, well, then this is right. But for our purposes, okay, we just want to leave this as 8 electrons around each one. Okay? And you might be asking, well, we saw a similar situation here where we had nitrogen, okay, that formed a double bond with an oxygen. I can't remember where we put it. And then we had 2 X's over here, then an X here, and then we formed a single bond here with this oxygen. And one of the things you might ask yourself, okay, is, well, that wasn't lithium, it was sodium, wasn't it? Okay? You might ask yourself is, why can't we do this when you just told us that some of these elements formed expanded octets? Well, where is nitrogen in reference to phosphorus? It's in the second period, where phosphorus is in the third period. This can do that, nitrogen cannot. So for our purposes, which one of these would you guess is more electronegative? Because what happens is fluorine is the most electronegative element on the table. Okay? So then which one is going to be more electronegative? Is it going to be nitrogen or is it going to be oxygen? It's going to be oxygen. So then what happens is, since this has a higher electronegativity, it pulls those electrons over just a little bit more, even though they're not bonding to anything. But this has a higher electronegative charge, so it's going to pull them a little further over, even though it doesn't look like you're forming a bond like you are here and here. And that's why this has to look this way, and this looks the way that it does here as well. All right. So we have some papers that are due tomorrow. Okay. And then I'm sure that this probably really wreaks havoc for a lot of people when they take this in college. I'm almost certain of that. And maybe there's a lot of things that does. And that's why we discuss things the way we do, approach things the way we do, so we are ready for that when we reach that next step. Okay, that's all I have. We'll catch up to you next time.